Hello. In this video, we discuss how two or more quantities affect each other. This is called variation. Let's get started. We begin by describing four types of variation that we could have in real life. The first is called direct variation. Direct variation is very common. For example, if I consider my cell phone bill, what is it actually linked to? Well, it goes up every time I go over my data usage. So my data usage, if I call that X, is the thing that impacts my cell phone bill Y. So they're directly related. As my data usage goes up, my cell phone bill goes up. So when we have direct variation, the equation that we're going to be using is Y equals K times X. Now K in each of these equations is called your constant of variation. Basically, in this case, it's the slope of a line, right? It's your constant rate of change in this case. So for example, if I have to pay an extra, let's say $20 for each extra gigabyte, I hope that's not what it is, I'll have to check my cell phone bill. This would be 20x, right? For each extra gigabyte that I use. So that constant K depends on your actual situation. But the idea of direct variation simply means as one quantity increases, that forces the other quantity to increase as well. They're directly going in the same relationship, so they're directly related. On the other hand, inverse variation works the opposite way, right? As one quantity increases, the other quantity must decrease. So when we say we have inverse variation, we could write, for example, that Y equals K over X. So instead of K times X, it's K over X. Some examples of this could be the more calories that I burn at the gym, the more my weight goes down. So the more I work out, it lowers my weight, right? Or the more kids you have, the less sleep you have, right? Those are inversely related. Joint variation, on the other hand, is when we're acknowledging that there's actually two components which are causing your value, your quantity, to increase. So this could be, for example, if you're trying to bulk up, maybe you take some protein supplements, maybe that's your X, the amount of protein that you're consuming, and then maybe Z is the amount of weight that you're lifting, and then that determines the amount of weight you put on, Y, right? So that's an example of where you have two components that are increasing in order to cause the third component to also increase. That would be our example of joint variation, a very common example. So joint variation's equation is just like direct variation, but instead of just one quantity affecting the increase or the decrease, now two quantities, like an X and a Z, are increasing that third quantity Y. Now, what really drives my students a little bit crazy is when we combine some of these, right? Because in real life, there's a lot of factors going on. It's really not just one thing that impacts another typically. So for example, a common one is actually the BMI. Okay, so the BMI, your body mass index, that actually depends upon, so if BMI was like your Y value, it depends upon two things. Did you know what they are? It depends on your weight, which is like the Z in this case, and it depends on the square, so multiplying by itself, whatever your height is. Okay, so it depends on two quantities. The more you weigh, that's going to make your BMI go up, so that's why it's on top. When you weigh more, your BMI will rise. So they're directly related, right? But the higher your height, right, your BMI goes down. So if you're short and overweight, your BMI is going to be pretty rough. So being short in this case is not fun for BMI. Okay, so that is an example of both direct and inverse variation together or combined. So you're going to have to pay attention as you're reading word problems about how quantities are known to relate to each other in order to build the appropriate model that describes the situation. So much of today will be just reading carefully and then writing the appropriate equation. So one more time, direct, they go up together. Inverse, they're opposites. They're going opposite directions. Their impact on each other. Joint, there's a couple of components that are impacting your quantity to go up or down. And then combined variation when you mix direct and inverse together. Okay, so let's take a look at our next slide where we put all this together. In example 1, it says, could you come up with a general formula for variation that is described below, where we're told that Y varies inversely, so I usually like to mark that, inversely, with some quantities, with the quantity the square root of X. Okay, now usually what they're going to give you is some sort of relationship. They've described the relationship, I boxed it for you, and then they're going to give you a specific example to help you make your formula more precise. Okay, so exactly how fast is this change occurring, basically? What's your constant of variation? So we begin by noting the first letter is Y, so I'm going to put Y equals. As soon as I see something varies, I put that letter first, and then I put the equal sign. Now, because they say inversely, should I keep my next quantity on the same line, or should I put it in the denominator? That's right, it would be in the opposite place, in the denominator. So this will be something over my next quantity. What is my next quantity? It's the square root of x. So as the square root of x goes up, y goes down, and vice versa. What else do we know? Well, there's a constant. There's a rate of change at which this is happening, and that always goes on top here, or first. So that's our constant k of variation. Right now, this is very generalized, right? We would say that y equals k over the square root of x describes the relationship between y and the square root of x, but we don't know how fast this is happening, and that's where k comes in. Is it 2 over the square root of x? Is it 10 over the square root of x? What is that constant rate of change? And so this is where the specific example of one situation, one point in time, will help us to fit into our graph so that we can get the right equation. So let's do that. Let's plug in our specifics to get our better, more precise equation. When y is 4, we're told that x had to have been 9. So that would mean that in our specific example, when y is 4, we'd have on the other side k over the square root of 9. But the square root of 9 we know is 3. We're trying to be kind to you here. So we have 4 equals k over 3. Much of these problems, after setting them up, is just basic algebra. Can you solve for k, right? Can you undo division? What's the appropriate operation that undoes division? That's right, multiplication. So we'd multiply both sides by whatever is underneath the k. That would be 3. A lot of students here get confused and they try dividing by 3 again, but notice that would make it k over 9 on the right, not just k. And we're trying to get rid of the denominator. So now we just have that k must be 12. So what does that mean? Well, now we know our rate of change in which this relationship is happening. We can plug back into our equation, and we now have that the situation that y varies inversely with the square root of x, it's tied together the following way. To get our y value, we'll have to take 12 and divide it by the square root of our x value. So as soon as we know our x value now, we know our y value. You can check out the Desmos link provided in the graph in the notes online on Canvas, and that will help you to actually visualize further what this graph looks like and how to make future predictions at various points in time. But this was the idea, using the words varies inversely to write the equation, using the specific information to find our constant of variation so we know how they're tied together at what rate of change. Let's head to another example for you to feel more comfortable. Example 2 says, could you write the general formula for the variation described below? Capital T could be time, right? Varies jointly, so I'm going to highlight jointly here, jointly with the cube root of x. Okay, we'll have to talk about what that means, and the square of d. And then it gives us some specifics again. T is 18 whenever x is 8 and d is 3. Okay, so how would you begin your variation equation? Feel free to look back at the first slide, pause the video, write it for yourself, and then come back and see how you did. All right, so because you had that t varies jointly, did you write t equals? First step, good. Then what's next? That's right, you need your constant of variation k. Now, k could either be over something if it's inverse relationship. It could be touching something if it's direct or jointly. And here it's jointly. So we will, in fact, be touching our next quantity. What's our next quantity? It's the cube root of x. Now, remember, cube root and cube are two different things, right? Cube root is like a square root, except instead of an index of 2, you have an index of 3. So this would look like the radical symbol with a little 3 up here. That's the cube root of x. So for example, if x was 8, the cube root of 8 would be what number times itself 3 times gives you 8? 2. 2 times 2 times 2. So the cube root of 8 would be 2. That's the idea there. Okay, well, since it's jointly, that's not the only quantity that's affecting t. It's also affected by the square of d. Notice it doesn't say the square root, but the square of d. So the square of a number meant that you took that number and you raised it to the second power. So the number would be d, and since it's joint variation, they're next to each other, so times d to the second power. This would actually be the equation that describes this relationship between the quantity t and what it depends on, the cube root of x and d squared. What was next after you have your basic equation laid out? That's right, you needed to plug in your specific information. So now let's find k. So to find k, we use our specifics. So what are our specifics? Well, t was 18, and now we're looking for k, so let's switch our color here so we can see that clearly. we're going to say we know t is 18 whenever x is 8. So that was the cube root of x, the cube root of 8. I already talked about that one by accident. And the square of d, so d squared. But d now is 3, so 3 gets squared. See if you can do the algebra yourself. Pause the video, come back to me, see how you did to find your k. All right, let's see how you did. On the left side, you had 18, and on the right side, we already talked about the cube root of 8 being 2, because 2 times 2 times 2 is 8. Most calculators have that button, by the way, but that one's easy. I hope you can do it by yourself. So that's k times 2, and 3 squared was just 3 times 3, which is 9. Well, this is quite a nice little linear equation, isn't it? We just have that 18 equals 2 times 9 times k. Remember, the order of multiplication doesn't matter for real numbers. That's called the commutative property. So we really just have that k times 18, or 18 times k, equals 18. So don't we know what k must be if you undo multiplication with division? Yeah, k is really what number? It's 1. So that's kind of a boring rate of change, but it is in fact the rate of change here. So now we have our equation. Now that we know that k is 1, we can now say with confidence that our equation that represents the relationship between t and the joint things that affect it, the cube root of x and the square of d, would be t equals, now do you have to write 1 times something? No, it kind of looks tacky. You could if you really want to. 1 times the cube root of x times d squared. If you wrote that, you get full credit. We know what you're saying. But since it is 1 times something, it's not necessary. So feel free to ignore writing the 1 times something. If it was 2 times something or half times something, it would be more necessary, wouldn't it? Again, I provided the link to the Desmos graph. You could also graph this in a graphing calculator so that you can see the trajectory that we're describing here, how t is impacted by the x and the d value in this joint variation problem. All right, let's have you try another one, see how you're feeling about variation problems. Here we go. A word problem, oh my. Again, most Americans do poorly on word problems because we give up too quickly. So when you're reading a word problem, remember there is information that you're looking for that you have knowledge of what to do with. So don't give up. Keep looking for the key words that are going to help you set up the right equation that models the situation and then solve the problem. Don't give up. Okay, you can do it. It says the amount of a drug is given in milligrams and it varies directly. So I'm going to mark that here with a color here. Let's do red. It varies directly with the weight of a patient. And this time we're giving the weight of our patient in pounds. Usually that's kilograms, but I was trying to be kind to you. Okay, so let's see what they've told us so far. The amount of the drug that you're going to give, maybe it's Tylenol, whatever it is, varies directly with the patient's weight. Well, that kind of makes sense, right? They're going up together or down together. The more the patient weighs, the more drug they need for it to be effective, and vice versa. So how could I begin this problem? What equation of variation could I write? Well, I could pick a letter to describe the amount of drug. So you could do D for drug or dosage, D. It varies, so it equals. Now, how does it vary? It varies directly. So as one goes up, the other goes up. So we'd use the K times our next quantity. What's the next quantity? So we did the amount of drug. It's the weight of the patient. So I could use W for weight. And now I have my model. Now, it's not a perfect model because we don't know exactly at what rate every drug would be unique here, right? How much you'd have to increase the dosage by or decrease it by, depending on the weight. So K could be 2, K could be 100. We don't know what K is. How did we find K again? That's right. We'd plug in the specific information we were given. So we're given that if we have a patient who weighs 150 pounds, so when W is 150, and they're giving us in pounds, so they're being consistent. That's very kind of them. Sometimes we have to make changes in our units. So when our weight is 150 pounds, then the dosage that was given was 250 milligrams. So D for dosage in this case was 250, and again, it's still in milligrams. They haven't changed any units on us. All right, so we could plug in that information, and this would help us to find our K value, wouldn't it? So let's do just that. We would now have that the dosage was 250, D is 250, K we don't know yet, so I'll put my color red for K. And then the weight that gave us that dosage of 250 was when a patient weighed 150 pounds. So 150 was my W there. So in that case, could you solve for K? Could you undo multiplication with division? I certainly hope so. So that would give you that 250 gets divided by 150, or 25 gets divided by 15 if you divide those 10s out. So let's see what you get here for K. Yep, did you get that k, when you did 250 divided by 150, the 10's canceled, the 5 goes into both 25 5 times and 15 3 times. So k was just 5/3, or if you prefer, 2 1/3. Is that right? No, goodness. I said it backwards, I apologize. 1 2/3. Sometimes I switch my numbers, I hope you don't do that. 1 2/3. Okay, so k could either be 5/3 or 1 2/3, or if you really like decimals, that's 1.6 repeating. We usually write that like this, okay? So those are the 3 different ways you could describe k. I will say most math textbooks and homework websites will want the improper fraction, but most humans prefer decimals. We understand them better. Okay, so once we have k, we now have our formula complete, don't we? Our formula for this situation that describes this phenomenon is that the dosage D varies directly with the weight of the patient, so it equals k times the weight, where k we just found, I'll use the fraction if you don't mind, 5/3 times the weight of the patient W, where dosage was in milligrams and weight was in pounds. So this was our model that describes the situation. So now if you have this model in mind and you go into a patient's room, maybe you're a nurse or you're an EMT or something, if you know that's the relationship for this particular medication, then as soon as you know the patient's weight, you can multiply it by 5/3 and you know the dosage for this patient. So you can check whether or not the pharmacy told you the right thing, or you can make the judgment call yourself if needed. Okay, so now it's asking you to answer one more question. Now that you have the model, the relationship between the two quantities, you're told to find the correct dosage that should be given to a patient who weighs 265 pounds. So what do we need to do now? That's right, simply plug in 265 for W. So our dosage for this patient in this example, when they weigh 265 pounds, would be 5/3 times 265, or the decimal version of things if you prefer. You end up, when you multiply 5 times 265 and dividing by 3, the decimal you get is 441.6 repeating. Or you could have said 441 2/3. It's the same thing. So 441 2/3 is equivalent. Whichever one you prefer there, it means the same thing. So this is how many milligrams that patient should be receiving. Because they weigh a little bit more, they had to get a higher dosage. That makes sense because it was direct variation. All right, well, we have one more problem. It's not medical related, but it is going to be familiar to some of you who studied geometry in the past. So let's take a look. It says the volume of a right circular cone, and I've shown you in the picture here, like an ice cream cone. Right circular means that it's not slanted, right? It has a right angle to the ground. Okay, so right circular cone, it varies directly, so how much volume you can stuff inside of it, it varies directly with the square of its radius around its circular base and its height from the base to the tip of the cone. Its constant of variation was discovered, so they're telling us what k is. How nice of them. Was discovered to be pi/3. Our job is to write the general equation for volume and then use it to predict the volume of the right circular cone when it has a height of 12 feet and a radius of 3 feet. Okay, so to begin, let's write out how this variation has been described for us. We've been told that the volume V, so I'm going to write V for volume, varies directly. So how would I write that? Yep, equals k times something. If it had been inversely, the next quantity would go in the denominator, right? It varies directly with the square of its radius, so that's r to the second power, and its height. So, and its height, well, that means this is really joint variation, isn't it? Right? We have two quantities that it's varying directly to. So we're given V equals k times r squared h, okay? So that was a discovery that was made when they looked at various volumes and how it was impacted by its radius and its height. Okay, but it's also telling me that they found k. They discovered that every time their constant of variation was pi, the irrational constant that's roughly 3.14 but goes on forever without repeating, is pi divided by 3, or pi/3. So now we could rewrite the equation, the model, as V equals pi/3 r squared h. Pi/3 r squared h. So there's our general formula that they've asked us for. What they're now asking us to do is use it to make a prediction. This is the easy part, right? Predict the volume of this cone if it has a height of 12 feet and a radius of 3 feet. So at this point, pause the video, plug in yourself, do a little algebra, multiplying and dividing, and see if we get to the same answer. Okay, see how you did. When you plugged in your specifics, you have an r radius of 3 feet, and you have a height h of 12 feet. So when you plug those specifics in, did you get that the volume of that particular cone, right circular cone, would be pi over 3 times r, which is 3 feet, so 3 feet times 3 feet gets squared, times your height, which is 12 feet. Now you might be wondering why I'm writing the units out. I just wanted you to see what's happening with these units. That's why I'm doing it. So let's take a look at what the results would be then. You would get that your volume equals pi over 3. That part's the same. Nothing's changed. But 3 times 3 is 9, so we have 9. But feet times feet, isn't that really square feet or feet squared? So our units just became square feet in parentheses there, times 12 feet. So what do you think our units will turn out to be in this case? Feet squared times feet. Well, if it was x squared times x, you would keep the base the way it is, and you would add the exponents. So if it's feet squared times feet, you keep feet as your base, and your exponent would be 2 plus 1, which is 3. In other words, we get units of cubic feet, or feet cubed. Okay? Finally, to finish this problem off, a couple ways to do it. Multiplication can be done in any order. So if you prefer, you could divide the 9 by the 3. That's probably what most of you would do. And you would get 3 goes into 9 3 times. So now you have 3 pi times 12. So if you have 3 pi next to a 12, 3 times 12 is just 36. And that's how you would get your answer of 36 pi. That's what we would call the exact answer, but the approximate answer would be if you actually took 36 and multiplied it by roughly 3.14. And when you do that, so you would get approximately 113.097. So I used the approximation there. That's the approximate volume you'd have for this cone when pi is about 3.14. All right, so we've done 4 examples today of practicing setting up variation problems which were direct, inverse, joint, or combined. They get more complicated in the practice problems, so make sure that you have a note card or somewhere in your notes nice and organized so you can tell which type of variation problem you're dealing with and can set up the appropriate equation and execute it. All right, good luck practicing. I'll see you next time. Remember, math is not a spectator sport.